It's a pleasure to have Leonardo Macarini from the Instituto Superior Técnico in Lisbon, who will tell us about closed orbits on symmetric spheres and dynamical convexity.
Okay, thank you very much. First, I would like to thank the organizers for the invitation to be here, to speak here. It's a pleasure. And second, I want to say that I gave a similar talk around 2 months ago in a conference in Italy, and a few people here were also at that conference, and so I apologize for the repetition. Okay, so this is actually an ongoing joint work with Victor Ginsburg. Let me introduce you the basic setup. So we consider the sphere, fixed dimension 2n+1, with the standard contact structure. And then, given a contact form supporting this standard contact structure, I denote by P the set of simple periodical orbits of alpha. What I mean, first, what I mean with periodical orbit of alpha, I mean the following. Well, I think everybody here knows it well. Associated to a contact form, we have a canonical dynamical system, which is the rib flow, given by is the flow of the rib vector field, uniquely characterized by the following two equations. So we have a contact form alpha. We have this vector field, rib vector field, that satisfies this condition. So it is in the kernel of the differential of the contact form. And the second equation is a normalization condition. So these two equations determine uniquely a vector field, is a rib vector field, and when I say a periodical orbit of alpha, I mean a rib periodical orbit. That is a periodical orbit of the rib flow. And what I mean with simple periodical orbit means that the periodical orbit is not a multiple, is not an iterate of a periodical orbit. Okay, so the number of simple periodical orbits is the number of geometrically distinct periodical orbits. Okay? And there is a long-standing conjecture, a very hard question in Hamiltonian dynamics that states that every contact form on the sphere of dimension 2n+1, always supporting the standard contact structure, carries at least n+1 simple periodical orbits. So at least n+1 geometrically distinct periodical orbits. Okay, this is a very hard question. Well, it's easy to see that this bound is a sharp bound because for an irrational ellipsoid, you have precisely n+1 simple periodical orbits, but we don't know in general if it's bound, if this bound holds for any contact form. Well, when the dimension is when n is 1, namely when the dimension of the sphere is 3, this is known. It was proved first by Christopher Gardiner Hutchins. The paper was the year is the year of the publication. Christopher Gardiner Hutchins proved this, and the paper was published in 2016. And in a joint work with Victor Ginsburg, Doris High, and Umberto, we proved this independently. And Liu Long gave an alternative proof using a result from my joint work with Victor, Doris, and Umberto. Okay, but the first proof actually was given by Christopher Gardiner and Hutchins. So the conjecture is true when the dimension is 3. So when n is equal to 1. Unfortunately, in higher dimensions, it's far from being known. For instance, on S5, we don't know if every contact form carries at least 2 periodic orbits. The bound on S5 should be 3, but we don't know in general if we have at least 2 periodic orbits, simple periodic orbits. It's a very hard question, okay, in high dimensions. Notice that I'm not assuming any condition on the contact form here. It can be possibly degenerate. So without any condition on the contact form, the question in higher dimensions is very hard and far from being known.
Do you know the Weinstein conjecture for S5?
Yeah, sure, Rabinowitz. For any contact form on the sphere supporting the standard contact structure carries at least 1 periodic orbit. It was proved first by Rabinowitz. Right? Any star shape in R2n carries at least one periodic orbit. But the multiplicity is very hard. Any question? Okay. So we have this problem that you have at least n plus 1 simple periodic orbits. It's known in dimension 3 when n is equal to 1. And in higher dimensions, it's a very hard question. Okay, but when we impose some conditions on the contact form, we know much more. There are much more information about the bound of the simple periodic orbits. So notice that there is a natural bijection between contact forms alpha supporting the standard contact structures, the standard contact structure and star-shaped upper surface in R2n plus 2, right? Such that, so given us a contact form alpha, you have a unique sigma alpha in R2n plus 2, such that alpha is a restriction of the Liouville form to sigma alpha. Okay, so you can identify contact forms on the sphere supporting the standard contact structure with star-shaped upper surface in R2n plus 2. In R2n plus 2. Okay? And then we say that alpha is convex if the corresponding star-shaped upper surface bounds a strictly convex subset. Okay? This is my definition of convex contact form. And it turns out that for convex contact forms, we know much more about, we have much better results for the number of simple periodic orbits, for the minimal number of simple periodic orbits. A remarkable result due to Long and Zhu shows that for convex contact forms, you have this bound. Okay, so is the floor, you have at least the floor of n plus 1 over 2 plus 1 for convex contact forms, any dimension. And the student of Long, 3 years ago, improved this result when n is even. So showing that, in fact, you have the staining of n plus 1 over 2 plus 1 periodic orbits. Okay? But you see, in principle, you can say, wow, come on, it's just one more periodic orbit. But this is a very hard question. So if you improve the result, even for one more periodic orbit, it's a very important improvement. It's a very important result.
Is there any way to say what method is used?
Sorry?
What method?
A good question. Index theory, a combinatorial argument using index theory. Index theory, there are actually two key tools. They use two key tools: index theory and variational methods. And they use convexity in both tools, both for the variational methods and for the index theory. And Liu Long Zhu in 2002 proved that if alpha is convex and invariant by the antipodal map, so you have this symmetry, then the conjecture is true. Namely, you have at least n plus 1 simple periodic orbits. So with this symmetry, we have the result. Any question?
And what are the methods for that one?
Sorry?
What are the methods for that?
So,
What are the methods used to...
the methods are the same. But the point is that, well, maybe you can ask how they use the symmetry appears in the, they also use variational methods, and the symmetry appears in the combinatorial argument using index theory in a highly non-trivial way. But the methods are the same. Variational methods and index theory. But the point is, convexity is not a natural condition from the point of view of contact topology. because it's not invariant by contactomorphisms, right? Of course, if you have a convex guy, think, for instance, in the case of the contact manifold is a circle, right? So you can have something convex here. The corresponding sigma alpha is convex. But then it's easy to see that you can construct a contactomorphism on the circle such that the corresponding symplectomorphism in R2 minus the origin sends this guy to another guy that is star-shaped but is not convex. So it's not a condition invariant by contactomorphisms. So the question is how to understand convexity from the point of view of symplectic topology. That's the problem. An alternative definition that was already mentioned by Umberto in his talk this morning is dynamical convexity, introduced by Hofer v. Alexander. Let me recall you the definition. We say that contact form on the sphere of dimension 2n plus 1 is dynamically convex if the colonies and the index of every closed orbit is at least n plus 2. It's not hard to see, as Roberto already mentioned this, it's not hard to see that convexity implies dynamical convexity. And the point is that dynamical convexity is a natural condition from the point of view of contact topology because it's invariant by contactomorphisms. The index of periodical orbits don't change under contactomorphisms. And it turns out that the lower bound that I mentioned before in the convex case, remember that I mentioned that Liu long proved that in the convex case you have at least the floor of n plus 1 over 2 plus 1, and Wang improved this result It turns out that this bound that we have in the convex case holds in dynamically convex context. It was proved by Ginsburg-Urel. Yes?
I'm a little confused because in your previous slide you used points that are bigger than n plus 2, and I think therefore...
Because of the dimension, because the dimension in Berto's talk was, the dimension of the sphere was 2n minus 1.
Okay.
He was in R2n. Now we are R2n plus 2. Okay? So that bound that we know holds that Liu long Wang proved in the convex case holds in dynamically convex context. Okay? It was proved by Ginsburg-Urel using Lütjenich-Neudman theorem and equivalent symplectic homology. Because in the convex case, in the non-convex case, you need to use some Floer homology to replace the variational methods that you use in the convex case. So the natural question is, well, we know from Liu long Zhu we know that the case that the contact form is convex and invariant by the antipodal map, then the conjecture is true. So the natural question, since we know that this lower bound holds in the dynamically convex case, can we extend this result to the dynamically convex context? In other words, is it true that if you have a dynamically convex contact form that is variant by the antipodal map, then you have at least n plus 1 periodic orbits, simple periodic orbits? That's the question. And then we started to think about it. And it turns out that we don't know how to prove this generalization assuming only dynamic convexity. We need to assume something stronger than dynamic convexity that takes into account the symmetry. Any question? So before introducing the definition, I need some. Before I show you the definition, I need to introduce some notation. So take totally degenerate symplectic matrix A, okay? In other words, all the values of A are equal to 1. And then we can show that A is exponential of JQ, where J is a complex structure and Q is a symmetric matrix with all eigenvalues 0. And then there is a result that you can find, for instance, in the book of Arnold Giventhal, Symplectic Geometry, I think in an appendix of the book, I think, I'm not sure, that you can decompose symplectically this quadratic form Q into a sum of terms of 4 types. So you have the identically 0 quadratic form that gives you the identity, okay? And you have this other, the second quadratic form, this Q0, given by this expression that appears only in dimension at least 6. And you have these quadratic forms Q plus minus. You know, these guys, okay? So you have these 4 terms. You can symplectically decompose the matrix such that you have these 4 terms for the totally degenerate symplectic matrix. Okay? And then we define B plus minus of this matrix as the number of Q plus minus terms. It's a bit technical, but it's very important. Okay? So it's the number of these Q plus minus terms. So we have these 4 terms, and it's very important for in this talk, these last 2 terms, Q plus minus. Yeah, you have a normal form. Yeah, you can have a decomposition, and then you have these 4 types. Okay, these 4 types of blocks, let's say, and then they have these special ones that are given by these quadratic forms Q plus minus, and B plus minus are the numbers of these terms in this decomposition. Okay. Okay, so I define B plus minus for a totally degenerate symplectic matrix. And for a general symplectic matrix, how I define this in a natural way, you just take the subspace whose complexification is the generalized eigenspace of the eigenvalue 1, V. And then I define B plus minus of a general symplectic matrix, P, as a restriction as B plus minus of the restriction of this guy of P to V. Okay? Just a few examples, at least in dimension 2, so it's just to have some intuition. So you see, in the case of the identity, of course, B plus minus is 0, because then you have the identically 0 quadratic form. And you see, for these guys, it depends on the nilpotent part of the matrix. Okay? And now, how I define B plus minus for a closed orbit? You just define B plus, given a closed orbit, gamma, B plus minus of gamma is just B plus minus of the linearized Poincare map. So of course, these numbers does not change under conjugation, so it's well defined. Sorry? It's something very technical. Well, I think it's better to explain later, but let me just say the following. If you know a little bit of index theory, if you know something about Bot's function, it's related to Bot's function. So this expression, b minus, sorry, b minus plus minus. Sorry. So given a periodic orbit, it's important this, right? This. If you know a little bit of index theory and Bot's function, what you can show is that this guy, this expression here, is 2 times the splitting number at 1 minus the nullity of the periodic orbit, which is the geometric multiplicity of the eigenvalue 1. What is this, guys, this splitting number? Well, it's a long story. I try to explain just in 2 minutes. Because associated to a closed orbit, or in general to a symplectic path, you have what we call Bot's function, which was defined first by Bot in the case of closed geodesics. It's a great work of Bot, and it was later generalized to general symplectic paths by E. Long, which is the following. So you have this closed orbit gamma, and then you can define from gamma a function defined on the circle. So this is the Bot function that takes values into z. So integer values. And this function has a lot of very nice properties. For instance, there is Bot's formula that tells you the following: that the index, the columns and the index of the kth iterate of gamma is equal to the sum of Bot's function at the kth roots of the unity of the circle. And what are the splitting numbers? This function has also the following nice property. It is continuous, except possibly at the eigenvalues of the linearized Poincare map that lie in the circle. So we have, since it takes integer values, so you have possibly have jumps only at these eigenvalues, and these jumps are the splitting numbers. So there is an interpretation of this expression in terms of the splitting number of the Bot's function. And that's what actually we use in the proof. Okay, so now I can introduce the notion of strong dynamical convexity. So take a group acting on the sphere, any group acting on the sphere. Okay, and a G-invariant contact form alpha. And I denote by PS the set of simple symmetric closed orbits. Of course, symmetric I mean that the image of the closed orbit is invariant by every element of the group. Okay? And then the definition is the following. We say that, sorry, it should be alpha, not sigma, okay? I'm sorry, it's alpha. We said alpha is strongly dynamically convex if the following holds. First, you have dynamical convexity. So it means that every closed orbit has index at least n plus 2. But now, for the symmetric orbits, we need an extra condition. What's the condition? This one. That the index plus that expression is at least n plus 2. Only for the symmetric orbits. Okay? So the condition stronger than dynamic convexity, but just for the symmetric orbits. Any question about this definition? This is really important. Okay, so strong dynamic convexity means dynamical convexity plus an extra condition on the symmetric orbits, namely that the index plus that term is at least n plus 2. Yes? Sorry, again, what was the question?
In case you have a symplectic path
Yes.
generated by a symmetric path of symmetric matrices which are all positive. This positive case, can you say?
So the positive case. I will say something about this. The point is that this is a very good question. The point is that if you have a positive, you mean a positive path, right? In the case that so you have a symplectic path. So it's given by this differential equation, right? We said that the symplectic path is positive when AT is positive definite. Then we say that the symplectic path is positive. And then it turns out that this is actually a very important point, is that the second iterate of a symplectic path, of a positive symplectic path, always satisfies this condition. I will talk about this later.
Is it really strictly convex or any?
Strictly convex. Everything here is strictly, I'm assuming strict convexity.
Okay. But does strict convexity imply strongly dynamically convex?
Yes, actually, this is one of the results. One of the results is that convexity, if you have a contact form that is convex and invariant by the antipodal map, then it's strongly dynamically convex. More questions about this definition? Yes. Because the dimension is different. Because in Humberto's talk, he was in R2n. The dimension of the sphere was 20 minus 1. Okay. Notice that this condition, this definition, strong dynamic convexity, is natural from the point of view of contact topology, because it's invariant by contactomorphisms in this way, in this sense, right? So if you have a G-invariant contact form that is strongly dynamically convex, then the pullback of this contact form, of course, it's no longer in general G-invariant, this pullback, but it's invariant by the conjugated action. And it's strongly dynamically convex with respect to this conjugated action. Notice that in the definition of strong dynamical convexity, we have to take into account the symmetry. Okay? So we have invariance, we have a natural invariance in this way, in this sense. Right? Because this, of course, the index plus that term is invariant by contactomorphism. Okay? And now we have the first result, which states the following. So we have any group acting on the sphere and have a G-invariant contact form, any action. And then suppose you have this. This is a condition a bit weaker than strong dynamic convexity. So instead of n plus 2, I'm asking the lower bound. The lower bound here is n plus 1. Okay? So under a condition a bit weaker than strong dynamic convexity, the conjecture is true. Okay? So if you have a G-invariant contact form for any action, any G action for any group G, and F closed orbit has index at least n plus 1, not n plus 2, and the index plus B minus B plus is also bounded by n plus 1, then we have at least n plus 1 geometrically distinct closed orbits. So in particular, when you have strong dynamical convexity, you have at least n plus 1 simple periodic orbits. Okay? This is the first result. Now notice that the group is any group, and you take any action. So in particular, you can take the trivial action, of course. But the point is that when you have the trivial action, then every closed orbit is symmetric. So then you need this condition for every closed orbit. But then you have this corollary, right? So under this condition for every closed orbit, now I have, because when the action is trivial, then every closed orbit is symmetric, then the conjecture is true. You have at least n plus 1 simple periodic orbits.
Did you weaken from n plus 2 to n plus 1?
Yes, definitely. Yes. Because you see, you just apply the previous theorem, but in the case that the action is trivial. But the point is that then you need this condition here now for every closed orbit. That's the problem, because for the trivial action, every closed orbit is symmetric. You have this. But notice that this is nice, because of course when the symplectic matrix, when the eigenvalue 1 is semi-simple, namely when the algebraic and geometric multiplicities coincide, then b plus minus both are 0, right? So in particular we got this. So suppose you have a dynamic convex contact form. Actually, you don't need dynamic convexity here. It's enough to assume that every closed orbit has index at least n plus 1. Suppose suppose that you have this dynamic convexity, or that every closed orbit has index at least n plus 1. And now assume, moreover, that the eigenvalue 1 of the linear Reiser-Poincare map of every closed orbit is semi-simple. Then we have at least n plus 1 closed orbits. Of course, this assumption is weaker than non-degeneracity, right? So in particular, actually, we prove that in the case that alpha is dynamically convex, in particular, you get that if alpha is dynamically convex and non-degenerate, then you have at least n plus 1 simple periodic orbits. Sorry? No, any dimension.
Is this proving that? So that proves again that there are two orbits instead.
No, because you need to assume that. Why?
There's only one. It's not degenerate. It's no, it could be.
Probably this is the case when it's an SDM, right? But no, the results here, the results are hold the n dimension. Okay.
Is the group K result should be degenerate? Wait, sorry, is it degenerate or non-degenerate?
You mean the corollary?
Yeah.
No, in the corollary, that's the point. I'm assuming only. It can be degenerate,
Okay.
but in the corollary, I need to assume that the eigenvalue 1 is semi-simple. This is weaker than non-degeneracity. Well, non-degenerate here, well, we say that a contact form is non-degenerate if the linear Reiser-Poincare map does not have eigenvalue 1. Okay? This is the condition of non-degeneracity. Here in the corollary, I'm assuming, so you can have periodic, you can have eigenvalue 1, you can have degenerate closed orbits, but you assume that the eigenvalue 1 is semi-simple. If it's not degenerate,
Does that imply that you get semi-simpleness vacuously?
sorry?
Right, if you don't even have the orbit of eigenvalue 1, does that imply that, like, if you just said let alpha be a non-degenerate dynamically convex contact form, then would your methods give you number p is greater than or equal to n plus 1?
No, sorry. The corollary says that if alpha is dynamically convex, but I'm not assuming here that's non-degenerate. I'm assuming instead that the eigenvalue 1 of the linear Reiser-Poincare map is semi-simple.
Right. I'm saying this is obviously stronger, or
This is stronger than this result.
right. It's a weaker assumption.
It's a weaker assumption.
Does it also include the assumption of non-degeneracy?
It also includes?
Like, if it's, is it okay to have alpha be non-degenerate?
Yeah, absolutely. Yeah, sure, absolutely. Yeah, if you don't have eigenvalue 1, then of course, yes. Yes. I'm just I'm allowing the generate closed orbits.
Okay.
So in particular, if you don't have the generate closed orbits, then it's okay. It was actually proved previously by Gut and Kang. Okay. But I'm assuming a weaker condition. More questions? Well, of course, you can ask if it's true that when the action is trivial, then convexity, that every convex contact form is strongly dynamically convex. I don't have a counterexample, but I strongly believe that's not true. In fact, there is a kind of linear example, which is the following. There is a positive symplectic path in R6, okay? So positive in this sense, okay? Such that you have this inequality. So in particular, if this symplectic path could be realized as a linearized Hamiltonian flow of a Hamiltonian flow of a convex autonomous if it can be realized as the linearized Hamiltonian flow of a convex autonomous Hamiltonian homogeneous of degree 2 along a periodic orbit, then the corresponding contact form would be convex, but not strongly dynamic convex with respect to the trivial action. Okay, so I strongly believe that I don't have a complete counterexample, but I strongly believe that convex contact form is not strongly dynamic convex for the trivial action in general. But it's true that under some natural actions, invariant symmetric convex contact forms are strongly dynamic convex. And this is the second result. So as I said before, if you take a convex contact form on the sphere, invariant by the antipodal map, then it's strongly dynamically convex. Okay? So in particular, we covered the result of Liu-Long-Zhu, that, right, this result, that every convex contact form on the sphere, dimension 20 plus 1, has, invariant by the antipodal map, has at least n plus 1 simple closed orbits. So now we have a symplectic proof of this result. So you see, when we try to generalize this result of Liu-Long-Zhu, we realize that we don't know how to prove this result assuming only dynamical convexity. But from some point of view, this is good news because what happens is that we realize that convexity implies more than dynamical convexity, at least in the symmetric case. And it helps us to attack the following question, which is a very important and hard question in contact topology that Umberto also mentioned in his talk today. Is this question. There are examples of dynamic convex contact forms that are not contactomorphic to convex ones. Right? It's a very important question and a hard question. And then, using this fact that I mentioned, that we realize that in the symmetric case, convexity implies more than dynamical convexity, we were able to give a positive answer to this question, at least in the symmetric case. So we have this result. So given any n bigger than 1, there exists a contact form on the sphere, dimension 20 plus 1, that is dynamically convex, but it's not equivalent to a convex contact form by a contactomorphism that commutes with the antipodal map, because we need to use the symmetry, and theorem 2.
So is that starting at S5 or S3?
S5.
Okay.
We don't know if we can construct this example in dimension 3. We don't know. And how is the sorry?
Is your proof constructive or not?
Yes, definitely. It's very technical, but the proof is this one. The point is this. What we prove is that what we construct is a dynamically convex contact form invariant by the antipodal map that is not strong dynamically convex. In other words, the construction is the following, more or less. We construct a contact form such that every periodic orbit has index, so it's dynamically convex, so every periodic orbit has index at least n plus 2. But the contact form is invariant by the antipodal map, okay? And there is a special symmetric closed orbit, a special one, such that gamma s it's a very technical construction. I will not give details about this construction, but that's the point. Okay, so I just can tell you that we start with a contact form which is dynamically convex except at one closed orbit, at this orbit, gamma s. So we start with a dynamic convex contact form that is, with a contact form that's dynamically convex except at one symmetric closed orbit. And then we make a perturbation of this symmetric orbit, of this contact form, such that this perturbation is dynamically convex, and you have this. It's a very technical construction. But the point is this, right? You have a dynamic convex contact form that's not strongly dynamically convex, and invariant by the antipodal, with respect to the antipodal map. So how you get the theorem once you have this? Of course, using theorem 2, right? Because if you have a contactomorphism that commutes with the antipodal map, then the pullback also commutes with the antipodal map. So if it's convex by theorem 2, it's strongly dynamically convex. But strong dynamical convexity is invariant by contactomorphism, so it cannot be convex. At least by a contactomorphism that commutes with the antipodal map. Is it clear? Of course, this raises the following question, right? So, as I said, when you have a convex contact form that is this theorem 2, right? When you have a convex contact form that is invariant by the antipodal map, then it's strongly dynamically convex. And now start with our example, right? We have this example of a contact form that is invariant by the antipodal map and is dynamically convex and not strongly dynamically convex. And now take any contactomorphism, phi. Then the pullback of this contact form of the example is invariant by the conjugated action. Okay, this is invariant by the conjugated action. So if you assume that this guy is convex, so it's invariant by the conjugated action. So if we can prove that every convex contact form that is invariant by a conjugated action, an action conjugated to the action generated by the antipodal map is convex. Sorry. If we can show, yes, if we can show that, if we can show that a convex contact form that is invariant by a Z2 action, which is conjugated to the action generated by the antipodal map, is convex, then we can drop the assumption that the contactomorphism commutes with the antipodal map in the previous theorem, right? Because we have this example of a dynamic convex contact form, alpha, that is not strongly dynamically convex. So take any contactomorphism. The pullback of this contact form is invariant by this conjugated action. If we can show that if this guy is convex, then alpha is strongly dynamically convex, then we can drop the assumption that the contactomorphism commutes with the antipodal map in the previous result. But so far, we only know to prove that if you have a convex contact form that is invariant by the antipodal map, then it's strongly dynamically convex. We don't know how to prove this for more general Z2 actions. Questions? So as I said, a positive answer to this question would allow us to drop the assumption that the contactomorphism commutes with the antipodal map. And then we would get really an example of a dynamically convex contact form that cannot be equivalent, that cannot be contactomorphic to a convex one. But unfortunately, so far we know we have this example only assuming that the contactomorphism commutes with the antipodal map. Any question? So these are the results. Now let me give you an idea of the proofs. First of theorem 1, the proof of theorem 1. Well, you asked before, what are the tools in the proof of the lower bound of the simple periodic orbits in the convex case, right? And I said that you use variational methods and index theory. And in this case, in theorem 1, of course, we also use index theory, but our variational methods are Floer theory, Floer homology. So the proof is based on positive equivalent symplectic homology and a combinatorial argument using index theory. It's crucial to use the so-called carry map, which is injective map from n to p cross n. Recall that p is a set of simple periodic orbits that satisfies this property. Where these numbers n plus 2m come from? They come from the fact that the positive equivalent symplectic homology of the sphere of dimension 2n plus 1, let me denote in this way, is isomorphic to, here I'm using the degree given by the columns and the index. I'm taking rational coefficients here, so it's isomorphic to Q when the degree is n plus 2, n plus 4, and so on, and 0 otherwise. So n plus 2m are precisely the degrees where the positive equivalent symplectic homology is non-trivial. Okay, that's the reason why I have these numbers there. And the index and the index plus nullity is that the local equivalent symplectic homology is concentrated in these degrees. And how this expression, right, this b minus b plus appears. This expression appears in this in the combinatorial argument. The point is that we need to use what we call the index recurrence theorem. It also follows from the so-called common index jump theorem by Long and Zhu that gives you a control of the index of iterates of periodic orbits for a collection of periodic orbits. This is a technical argument, okay? The idea is just to show you how the point is just to show you how this expression appears in the combinatorial argument. Because you have this control of the index of the periodic orbits. I mean, of course, in the proof, you assume that you have finitely many orbits, R periodic orbits, and then you have to show that R is at least n plus 1. And then you have this control of the index of the periodic orbits. And then you have this expression here. That's why I need the control of this expression in the argument. Okay? Because of this control. This is very technical. Okay? I'm sorry, I cannot give details about this. But if you want, we can talk later. Okay? But of course, then you can ask why you need this control only for the symmetric orbits. The point is the following. You need this control only for the symmetric orbits because the orbits that are not symmetric appear at least twice. That's why you need this control only for the symmetric orbits in the argument. Okay? This is a very technical argument. You use index theory, Bot's function, a lot of things. But that's the point. You need this. You need a control of this guy because of this index recurrence theorem, okay? And you need this control for the symmetric orbits only because the symmetric ones appear at least twice and with the same index and nullities, of course. So you need the control of this guy only for the symmetric orbits, okay? So this is just a rough idea of the proof of theorem 1, okay? So it uses equivalent symplectic homology and a combinatorial argument using index theory. And now let me give an idea of the proof, a sketch of, a rough idea of the proof of theorem 2, that convexity implies strong dynamic convexity. So you take alpha, a convex contact form, which is varied by the antipodal map. And now you take the Hamiltonian homogeneous of degree 2 such that the corresponding hypersurface is the level 1 of the Hamiltonian. Okay? Since alpha is convex, H is convex, and it's moved away from the origin. Okay? And by the invariance of alpha, H is invariant by the antipodal map. And now take any closed orbit of alpha. Okay, so it corresponds to a Hamiltonian closed orbit of H on the energy level 1, sigma alpha. And let gamma be the linearized Hamiltonian flow along this periodic orbit. Then it's easy to see that the index of the orbit as a Rib orbit is the index of the Hamiltonian, of the linearized Hamiltonian flow plus 1. Something easy to see. Okay, using the fact that H is homogeneous of degree 2. Since H is convex, whenever you have a positive symplectic path, this is a general fact. When you have a positive symplectic path, then it's well known that the index of this guy, the Collins-Zenner index, if the path is you have a path, so this is a path yes, P2n plus 2, then the Collins-Zenner index of this guy for any positive path, it's a general fact, is at least n plus 1 for any positive path. So the index of the linearized Hamiltonian flow is at least n plus 1, so it implies by this relation here, this implies that the index of every closed Rib orbit, now here is the index of the closed Rib orbit, so it's a linearization of the Rib flow along the contact structure, is at least n plus 2. So this implies, this is an argument to show that if the contact form is convex, then it's dynamically convex. But the question is why it's strongly dynamically convex. The point is this. So now suppose that gamma is symmetric. Since H is inverted by the tip of the map, we have that the linearized Hamiltonian flow is the second iterate of the linearized Hamiltonian flow along half the orbit. That's the point. Why it's true? I'm using here strongly that H is invariant by the tip of the map, because the linearized flow, the gamma, the linearized Hamiltonian flow, it satisfies the following equation. It's given by the corresponding symmetric matrix is given by the Hessian. Satisfies this equation. But since H is invariant by the tip of the map, only in this case, what happens the following is that the Hessian of H. It's a Hessian of H at gamma t. But since H is invariant by the tip of the map, we have that the Hessian of H at x equals the Hessian of H at minus x. Because it's invariant by the tip of the map. When you take the second derivative, you cancel the minus sign here. So we have this relation. And this implies that for a symmetrical orbit, the linearized Hamiltonian flow is a second iterate of the linearized Hamiltonian flow along half the orbit. That's the point. Okay? Then, as I said before, we have that since H is convex, we have that the index of half the orbit is at least n plus 1. Because it's a positive path. Okay? And it turns out that this implies, that whenever you have this, we have a symplectic path such that the index is at least n plus 1, then the second iterate of this path satisfies this relation. That's the point. And then using this, you can show, using that the relation between the index of gamma and the index of the linearized Hamiltonian flow, and this relation between the b plus minus, you can show this. Okay? Any question?
What goes wrong with this when you do the other action? So the conjugated.
It's a very good question, but because of this point, because you have this only for the tip of the map, when it's variant by the tip of the map. When you have in general as a Z2 action, suppose that you have a Z2 action generated with this generator, phi. And you have that H is invariant by this phi. It's not true in general for any phi that the Hessian of H at x equals the Hessian of H at phi x. It's not true in general for any phi that generates a Z2 action. It's true only for the tip of the map. That's the point. So in general, when you have a Z2 action, it's not true that the linearized Hamiltonian flow along a symmetric orbit is a second iterate of the linearized Hamiltonian flow along half the orbit. This is true only for the, in general, well, it's true only for the tip of the map. That's the point. So I think I read over time. Just this is the last. If you give just one more minute. So you see, we use it heavily the fact that Z2x is generated by the tip of the map because of this, right? However, when n is odd, it means that the corresponding real projective space has vanishing first-hand class. We have a more flexible proof that allows us to consider more general Z2 actions. And I think, I'm not completely sure. I'm 99% sure. But I think that using this more flexible proof, we can improve the example in theorem 3, where I assume that the contactomorphism commutes with the antipodal map, assuming a condition on the contactomorphism that is C1 open. More precisely, I think, I'm not completely sure, that we can prove this. We can prove that given any n bigger than 1 and odd, there exists a Z2 invariant dynamically convex contact form, alpha, such that given any contactomorphism phi that commutes with the generator of this action, of this Z2 action, then there exists a C1 neighborhood of this guy, such that any contactomorphism in this C1 neighborhood, if you take any contactomorphism in this C1 neighborhood, the pullback of alpha cannot be convex. So it's not, this alpha is not convex by any contactomorphism in this C1 open subset of the group of contactomorphisms. That's how I stop here.